So we're starting our material for exam 2, and we're starting with chemical equilibrium. And all of nature is trying to achieve chemical equilibrium. So it is pretty applicable because every situation falls into that category. But here's a couple pictures that, these things happen in nature. Oh, Jackie, what's wrong with these pictures? All right, you've got what I mean is what's wrong in the sense that they don't match what equilibrium really is. Chemical equilibrium. Why? What's that? Well, these things are, it's natural that that rock is like that. It's natural that the guy tumbles down the stairs. It's just chemical equilibrium, right? Is it just that arrow? No, it's also going back too. So it's supposed to be going back and forth. What's the word for that? It starts with the D. Not damn it. It's dynamic. Equilibria are dynamic. They go both ways. So these pictures aren't good indicators of chemical equilibrium because they're not dynamic in that sense. The thermodynamic equilibrium constant, big K. Now I've changed things already, Sabina. You're going to notice that already. So in the little handout's not going to perfectly match. But how do we write an equilibrium constant expression for the below reaction where little a, b, and c are the blank coefficients? What were they called? Start with an S. Stoichiometric. You remember that? Stoichiometric. They're the stoichiometric coefficients. Okay. Oh, well, that's our reaction. So, Kelly, if that's our reaction, how would you write the equilibrium constant expression? Big K is what over what? Products over reactants. Raised to there, everybody? Stoichiometric coefficients, right? So what would it look like? Kelly gave you some guidance there, Marlena. What would it look like?
On top C.
Big C. Now, is it brackets? What do the brackets mean? Concentration, okay.
And then
To the little c.
And then the bottom would be in brackets. Oh, yeah,
Yeah, sorry, I wrote the wrong one first. Okay. Right? There's how we write our equilibrium constant, big K expression. Kimberly, an equilibrium constant is just a number. Okay, and there will be some significance to that number. But does that number have units? Yeah, she's right, it doesn't. And a hint that it doesn't have units is look what we're going to be doing here. Right? You take an E, that E, and raise it to some number, you're not going to get units. Right? Or you could get rid of E, right? Remember, how do you get rid of a little e on both sides? You have to do what to both sides? Take it to the log, the ln. So you end up saying, oh, ln, okay, and you can solve for, it would be that. So just playing around with the math, you can't, this has to be unitless. Right? It doesn't make sense for it to have units, mathematically. So what's going on there? It doesn't look like the units would be canceling. Sometimes they might, but there's no guarantee. This is probably a PChem question, Jeffrey, but I don't think we've talked about it in PChem yet. Why? I guess. I didn't really ask anything. Why are these equilibrium constants unitless? Has something to do with standard states. Anybody know? Has something to do with standard states. What is a standard state? Well, what's going on here is really whether you have, I mean, these are the three things. These are the possibilities. Either it's a gas, a solute, right? A solute is something dissolved in like water or something. It's 2 molar, right? Or it's a solid, it's a liquid. That covers pretty much everything. What are the standard states? For a gas, it's 1 bar. For a solute, it's 1 big M. Big M stands for molar. A solid, the standard state is just be pure. And for a liquid, the standard state is just be pure. Now, what's the big deal? Why? Well, when you plug these numbers, these concentrations, all right, or whatever you're plugging into your equilibrium constant expression, raising it to the stoichiometric powers, it's always a ratio with respect to the standard state. So if it's like here we have concentration of C. That means it must be a solute. So the units had better be big M, because whatever the concentration is, we're really dividing it by 1M. And we never do this. This is something that we never bother doing. If in our equilibrium constant expression we have a gas, well, you plug in the pressure of that gas, it had better be in units of bars, because you have to divide it by 1 bar. So the units always end up canceling. If you have a solid in this equilibrium constant expression, you plug in, or let's talk about a liquid instead. If you have a liquid, water. What is water's concentration? Pure water. Does it have a concentration? Concentration is what over what? Moles over liters. So take pure water. Just take a jar of it. You have so many moles of it. You know the volume. Darn right, water, every liquid has a concentration. Water is 55.4 molar. So you have pure liquid water in this reaction. So you have to write literally 55.4 molar, right? And then divide it by the 1 molar. Now we're not going to be doing that. We're going to see why in a little bit. But the units need to cancel, okay, with the concentration of the pure. So really, but we're talking about a pure liquid, so it'd really be 55.4 molar divided by 55.4 molar, technically. So what I'm getting at is something that we're never going to do and we're never going to see. We're never going to write all of our concentrations, whether it's a gas, solute, or whatever. We're never going to write with respect to its standard state. We just leave it out. But we shouldn't, because that's how the units all cancel out. And we shouldn't, because when we start talking about gases, it's the reason why we have to have our units in bars. It's the reason why we have to have our concentrations in big M, because we're dividing it by the standard state, and we never write that. Okay? So there's reasons why we're kind of stuck with those things. Now, what is left out of all equilibrium constant expressions? If what's in the reaction? Liquids, pure liquids, and what else? Pure solids. Pure liquids, pure solids. Why? Because essentially you're dividing them by their standard state, and their standard state's it's pure. So their standard state is the same as what's in the reaction. So you have H2O. If H2O liquid is in your reaction, you should literally be writing the concentration of H2O liquid, right, in your raised to its stoichiometric power in your equilibrium constant expression. But you're dividing it by the standard state, which is pure water again. It doesn't matter. Solid, same story. It just cancels out on you. Okay. So we don't even bother with these. Manipulations with equilibrium constant expressions. So if I lost you somewhere along here, just ask. You played around with this a little bit, but let's see if Desiree remembers this. If this reaction up here is flipped, right? This reaction, we flip it. So the reactants now become the products become the reactants. What will be the new equilibrium constant for the flipped reaction? What happens to that K? What happens to that K? right? Essentially, we're going to flip this side. Well, if you flip to this side, you pretty much got to flip that side. So it would just be not K anymore, but 1 over K. Just be 1 over K. You flip one side, you got to flip the other side. Okay? So flip a reaction, it pretty much just flips the equilibrium constant that you had for that original reaction. Okay, let's take 3 reactions. And what we're going to do is add them all up and get an overall reaction. Okay, so I maybe remember playing this game, right? You take 3 reactions, right? And then you play the game. You cancel what you can. Stuff cancels here, cancels there. Remember doing this kind of thing? And then whatever you ended up with ends up down here. And you have an equilibrium constant for that one, equilibrium constant for this one, equilibrium constant for this one. Now my big K, how is this, the K of this reaction? We canceled all this stuff out. How is it even related to K1, K2, and K3? How is it related? The equilibrium constant for the summed reaction is just the, does anyone remember? It's the product. Someone remembered. It's the product. So my big K would be K1 times K2 times K3. And when you could see that they're going to cancel out here too, because you could write in their equilibrium constant expressions for K1, K2, and K3. And since they're all being multiplied, yeah, stuff is going to cancel. If you cancel it over here, it's going to cancel when you multiply it too. Okay. Equilibrium and thermodynamics. If a reaction is spontaneous, what does that mean in the world of thermodynamics? Okay, let's see if this works. I had a little thing going here. Okay. First, there's a hint of what I'm getting at in this diagram, which you don't have in your notes. And it's a plot of free energy. Free energy? What the heck? What symbol was free energy? That was delta G. Now, what good was delta G? Spontaneity, right? Spontaneous reactions. What happened to my audio cord? You guys aren't going to have sound. Well, no sound. I'll make the noise for you. So the point is spontaneity is it going to happen or is it not going to happen, right? And do you remember that game? If delta G was what? That's what you're always, oh, you want this protein to happen, for this to happen in the cell. That delta G for that process needs to be negative, right? Negative meant that it was going to be spontaneous. So here's an example of spontaneity. You have diamond, right? You have diamond rings. And this is its energy. This is its potential energy right there. That's the potential energy of this diamond structure. Well, carbon dioxide is way down here, right? That's just the energy of carbon dioxide. So shouldn't diamond just spontaneously go to carbon dioxide? True or false? Diamonds spontaneously go to carbon dioxide. True. It's just the word spontaneous doesn't mean what?
All at once.
Right? It doesn't mean immediate. It means probably in 100 to 500,000 years. Yeah, it's going to be gone. Okay? Why does it take so long? It takes so long because of this huge thing, and I can't really draw it to scale because I didn't want to use up the whole paper. What's EA? Activation energy, the energy barrier, the energy that those reactants need to have in order to get converted to products. Yeah, products is at a lower energy, but how are you going to get there? You have to overcome this energy of activation. It takes a long time, unless you use a hydrogen torch, and you can overcome it. Let's see if this works. Okay, now, okay, I got to be the guy, right? we bought this piece of diamond on eBay for $200. It was only $200 because look at it. See, you said something like that. Nobody wants that on their finger. So now we are going to try to burn it with our hydrogen torch. As you see, it's changing color. Now this is a great physical chemistry observation here. The color change. Did you notice? It was kind of dark yellow, it's turning bright yellow, now it's turning white. That's black body radiation for you. But it takes forever to get it to burn. Now you can see little blue flames here. It is burning a little bit. You know, and when you burn it, you get carbon dioxide. But it's a very high energy of activation to overcome.
Now we can just figure out how to do that in reverse.
Yeah, exactly. Reaction spontaneity depends on 3 factors. Now the equation gives you a hint for what reaction spontaneity depends on, Melissa. What are those 3 factors? All right, because we said delta G, I think the class already said this has to be negative, right? So what 3 factors does spontaneity, whether something's going to happen or not, chemically speaking, what 3 factors does it depend on? The hints in the equation. Enthalpy. Now what were the words for enthalpy that made sense, Jeff? What did we refer to a reaction and then refer to its enthalpy. There's 2 words. Both of them start with an E. Yeah, the energy of a reaction. It could be what or it could be what? It could be exothermic or endothermic. Those words all have to do with delta H, right? So enthalpy, whether it's exothermic or endothermic. Brandy, another parameter would be another temperature. It's in the equation, so it has something to do with spontaneity. Delta S, Naya. What is delta S? Starts with an E. And entropy. Entropy. Okay. So what would you want these numbers to be if you want this process to be spontaneous? Gloriana, what would you want the delta H number? These are all numbers. If you want it to be more spontaneous, this delta H should be what?
Positive.
Make it positive? Everybody agree? If you make it positive, will that make delta G more negative? No, it's the other way around, right? So not endothermic reactions, but exothermic reactions are, in general, going to be spontaneous. But you could have an endothermic reaction, that's fine, but then T delta S has to take over. Okay, so how about temperature? Temperature should be, Monica, what? To make it more spontaneous. Positive and really high probably, right? High. Entropy. Andy, that delta S should be what? Positive or negative or what? If you want to have a spontaneous process. If you want it to be spontaneous, delta S should be, what kind of number can you put in here and get delta G to be negative? It's minus T delta S. So don't, positive, because you don't want to lose that minus sign. So keep it positive. Increase the entropy. Okay, and again, this thermal is a p-chemish, physical chemistry sort of thing, but let's just leave it at entropy is not taking chalk and right, crushing in the parts. No, entropy is states and having a lot of different states, and we'll just have to leave it at that because it takes a lot more discussion to go any further, really. Okay. Oh, we already answered this, Danielle. Delta G is what for spontaneous reactions? Is negative, which is going to be yeah. Someone said it. Oh, Brandy said it. Less than, right? Oh, you read the whole. You guys know what I mean, right? Less than 0. How do we get values for enthalpy and entropy, Sabina? Where do you get this stuff? Tables, yeah, tables. Okay. The equilibrium constant and our delta G, right? So it's in there. Did you notice it? It's right here. These are changing Gibbs energy from our products and reactants, so it's in there, right? It's just the difference. Okay. Now, we already said little e is that exponential. What is, Kelly, how about, oh, there's no, yeah, let's talk about it. Big R, what's big R in this? Where'd Kelly go? What's that big R? Yeah, it'll be given. What is it called? We had it, we saw it before. I'll give you a hint. We saw it in this. What was it called? The what constant? Gas constant. Right. Okay. And what are units for energy? Joules. So when you pick an R for this expression, make sure you use 8.314 joules per Kelvin mole. All right? 'Cause there's a number of different R's you can pick. This is the one you want because it has joules in it. Okay? So that means T, when you plug it into that equation, Marla, T had better be in what units? This T had better be in what units? If you're going to use this R, T had better be in what units of temperature are in that expression? Kelvin. Kelvin. So temperature had better be in, everybody? Kelvin. Yeah. How about when you use tables, if you use tables to get this? Does anyone remember doing this? What units do you usually look up? It's per mole. It was kilojoules. Something wrong with that. You don't want it in kilojoules per mole. You're going to have to convert it to joules. All right? So just realize that in the homework. Otherwise, you can get really frustrated. The more spontaneous a reaction is, then K would be, what would you say, Kimberly? The more spontaneous a reaction generally is, you would expect K to be really, now K is what over what? K is products over reactants. If something is spontaneous, would you expect a lot of product or a little bit of product? A little bit, really? I'd expect a lot. If it's naturally going to occur, right? If this process is naturally going to happen, you would expect there to be a lot of product. I don't know when it's going to happen, but you should, and the more spontaneous, more product. That means K should be big, right? Because Ks are products over reactants. All right? Make sense so far? The more spontaneous your reaction, then you would expect the change in Gibbs energy, Ricky, to be...
Oh, I'm sorry. You're talking about the next one?
Yeah.
Oh, that's more.
Yeah. So this concept of more spontaneous, just realize it's coming up in your homework, right? That's how they're going to be talking. Le Chatelier's principle. Desiree, what's Le Chatelier's principle? Here's a hint of what's coming up. They have this reaction and they're doing stuff to it. All right. Does anyone have an idea? Gloria, you have an idea? Everything's hunky-dory. Maybe the equilibrium constant, let's say K is really small. Just pretend. K is really small. So we have just a little bit of reactant, but we have a little bit of product, a whole lot of reactants. But it's at equilibrium, right? So maybe draw the arrows more like this, right? And so that means the concentrations aren't changing over time. So But you can mess with this. You can remove some reactant. You can remove some product. You can add some reactant. You can add some product. Whatever you do that messes with a reactant or a product, now you screwed up the equilibrium. Now it's got to go back. Well, is it going to shift towards product to get back to equilibrium? Or is it going to shift towards reactant to get back to equilibrium? When is that at equilibrium? It's when you get that K number. Well, and K was called the equilibrium constant. So when you divide the products over reactants, raise to their stoichiometric powers, and get K, you're done. These concentrations aren't changing anymore. Now, it's still dynamic, but all that means is the rate of formation of products is the same as the rate of formation of reactants. So, but the concentrations aren't changing anymore. But if you mess with it, like in this example, it has to, you just screwed up, you're not getting K anymore. So if you don't get K, things got to move around and shift. For example, here's a big, long reaction. It looks like it's exothermic. The above aqueous mixture is at equilibrium. And the answers to these questions are, will we get more or less of the bromate for each case? So, or I guess you should say, or no effect. That should be another choice. So the first one, we're adding sodium bromide to the mixture. Now, Melissa, the game here is try to find some commonality, some way that it's influencing that reaction. If there's no influence at all, no commonality, then there would be no effect. Is there a commonality going on there? You're adding sodium bromide solid. What is it? Let me be a devil's advocate, though, right? I don't see NABR anywhere up there, right? I do not see NABR. NABR is an ionic compound. I can go through this whole big story. It's an ionic crystal, and it's, bromide's in here. But what's the rule? What's that one solubility rule that I'm saying, oh, please get in your head and just burn it in there? You put anything with Na, all it does is just get it in solution, right? That's the sole purpose of those alkali metals. When you see them, my brain doesn't even see it. My brain doesn't look at alkali metals because you don't want to. It just confuses life. So when I see that, I say, oh, I'm adding bromide, right? If I'm adding bromide, Melissa's exactly right. I'm adding bromide. I just messed up the equilibrium. So if I messed up the equilibrium, the next question I ask myself, Jeff, is to really help myself out, because it's going to get more complicated than this. I ask myself, do I have too much product or not enough product? If I add this bromide,
You have too much product.
I have too much product. If I have too much product, I'm going to shift towards what, Brandy? If I have too much product, I'm going to shift towards reactants, right? So if you use the words products, reactants, too much, too little, it takes a lot of the complications out. I got to shift towards reactants. Well, that means I'm going to have what? Bromate. Everybody. I'm going to have more. Okay. Write down your answers for 2, 3, and 4 here. And we'll see if you agree with Monica. Monica, how did you answer the first one? They're adding a small amount of sodium phosphate, which precipitates chromium phosphate. You end up with more or less bromate. It says less. Does everybody agree? So we're precipitating out chromium phosphate. I think everyone sees that that's this guy, right? You see that? So are we getting more or less of this? Less. So now you have a hole here. So now I guess it doesn't make sense to really talk about product anymore. It makes more sense to talk about reactants. So do we have too much or not enough reactant? Not enough. I forget what Monica said already. It's got to shift towards reactants to make up that difference. Okay, I forget if that's what you said or not. But it's got to shift towards reactants, so that means we're going to have more bromate. Okay. How about 3? Gloriana, what'd you say for 3? More or less bromate? Oh, I got to get this guy back here. Why? I don't see hydroxide in there anywhere. I don't see sodium ion in there anywhere.
So it will not affect less.
Remember, I'm not the nicest guy around. Does it interact with, will hydroxide interact with any of this stuff? It'll interact with the hydrogen, right? Most definitely. It'll make what? Water. So this is gone. Well, now, which way is it going to shift? Andy, which way is it going to shift? We don't have, if we want to get that equilibrium constant number, we have no idea what it is, but you have to get that K number. Well, now the hydrogen ion is too small. We need more of it. It's going to shift towards the right. It needs more product. So that means we're going to have less bromate. The last one. We're adding acetic acid. I kind of gave you a hint there, Jackie. We're adding acetic acid. More or less bromate. It's an acid, though. And we haven't talked about this too much. I mean, we haven't really got this far in analytical. But if you say something is an acid, I don't know if you even recognize this. This is vinegar. This is acetic acid. But you don't even really need to recognize the name. Just recognize the what out front. The H. There's an H out front of this organic thing, and it's acidic, right? You have this anion with this H. It's acidic. So if it's an acid, then it generally just has a lot of H pluses. It's donating. It's creating them in solution. Well, if you have more H pluses, now if you calculate the equilibrium constant, it's going to be too big. It's got to shift. It's going to do what? Shift to the left. Get more bromate. Okay. Now, why is this Le Chatelier guy a big deal? Because usually something in this reaction is really expensive. So you mess with the system until you get the optimal conditions for that most expensive part of the reaction. Okay? Or you're trying to generate one particular thing. Okay, so you play with the equilibrium, Le Chatelier's principle. Here's another one. Again, a Le Chatelier problem. Will you have more or less ammonia? Okay. First, we're heating it. Danielle, we're heating it? Before it was kind of nice, Danielle, when you try to find something that matches, right? It's kind of nice. But heat? It'd be kind of nice to write the word heat in there. Because then, if we're heating it, that means we're adding this heat. Right? So in this reaction, where could you write the word heat? Danielle, where could you write the word heat? Is it a reactant or a product? Jeff kind of gave us a hint. I think it was him. This is an endo or exothermic reaction. It's negative, so it's exo. If it's negative, delta H is negative, that was exo, right? It's kind of like going back to this delta G expression, right? If this is negative, those exothermic reactions are, more spontaneous, right? Whoa, right? So if it's exothermic, we can literally write the word heat as it's giving off heat, so write it as a product. Write the word heat in there. That's the only way I can figure these out. I write the word heat in there. And now I recognize where it's at. Because in this problem, Sabina, I'm adding heat. So now I have too much what? Reactant or product? Too much. Well, I wrote heat over here, though. I have too much product, right? Because heat literally is a product. Exothermic reaction. So I just wrote the word heat, just pretending like it's water or something, right? It's another product. Well, I'm adding heat. So now I have too much product. If I have too much product, I gotta shift that way. So that means I'm going to have more or less ammonia. Less. If I'm after ammonia, that's not going to help anything. Okay. So I want that temperature to be cold if I want to be generating ammonia. An inert gas, the pressure. Pressure they can play around with. Kelly, do you remember the trick to doing this? I think we spent a microsecond on this in general chemistry. And there was a trick to doing it. Does anybody remember? You're increasing the pressure. You have to count the what molecules on each side?
Gas.
Count the gas molecules. Because what can create pressure? Only one state, and that is the gas, right? Solids and liquids? No, they just lay there on the bottom. Right? Yeah, they have some headspace to them, but not a whole lot. It's the gas molecules that generate pressure, right? Collisions, force per unit area. So with their collisions with the container. So what we're going to do is figure out which side is the high pressure side. In other words, which side has the most gas molecules? Which side has the most, well, Marlene, let's look at it this way. The reactants. How many gas molecules do I have on this side? Nitrogen gas molecule. We're just pretty much adding up the stoichiometric coefficients for the gases. So you've got a 1 and a 3, 4. You have 4 gas molecules on this side. And on this side, everybody, you have 2. So you have a high pressure side. That's how I look at it. So if the system wants to generate pressure, it's going to shift towards the high pressure side. If the system wants to reduce pressure and relieve it, it's going to shift towards the low pressure side. Okay. So what we're doing to mess with this system is we're adding an inert gas. All that is doing is just increasing the pressure. It's kind of like taking a piston. But I guess this is just cheaper. How do you write pressure? Increasing pressure. You could just take a piston and increase the pressure that way, but a lot of times they do this instead. They just add an inert gas. It increases the pressure. Well, if we increase the pressure, the system has to respond by relieving that pressure. It's going to shift towards the product, the low pressure side. So that means we're going to have more ammonia. So that's a good thing if that's what they want. Okay. One more topic here before we have problems. Kimberly, we started way up here, and we could calculate that equilibrium constant expression. We could, but they better give us these concentrations when the system is at equilibrium. Otherwise, you can't calculate the equilibrium constant, right? That makes sense? So if you want to get the equilibrium constant, this system had better be at equilibrium so you can plug in the equilibrium concentrations. Yeah, right? No, it doesn't make sense. Now, what if it's not at equilibrium? If it's not at equilibrium, will you get K? No, you won't get K. So if it's not at equilibrium, you're not supposed to write K. You're supposed to write someone big Q. And we called it the reaction quotient. Okay? It was getting that big Q. All right? And again, it's the same. It's products over reactants. Products over reactants. It's an equilibrium constant expression. It's just that you're not at equilibrium, so you can't write K. You got to write big Q. Okay. So you calculate this big Q. Big Q is smaller than your K. Then to achieve equilibrium, it's going to shift towards products or reactants. You calculate a big Q. It's too small. Think in terms of products, because K equilibrium constant is always products over reactants. If Q is too small, do you have enough product? No. Yeah, you don't have enough product. If Q is too small. So you got to make more products. That's a shift towards products then, right? Then it'll shift towards products. If Q, calculate your Q, and it's bigger than K, right, then you have too much product. Well, then it has to shift the other way, right? Shift back towards the reactants. There's only one possibility left. Q equals K. Well, then you're at equilibrium. Okay. So that stuff will be coming up in the homework too. Okay. Let's try this one. Assume K is 200. What if the initial concentrations consisted of all that? Is the system at equilibrium? If not, which direction would the reaction shift? We should have a little L on here. That's why it doesn't show up. Right? So we've got a lot of plugging and chugging to do here. So this, you see that this is a Q problem, right? Reaction quotient problem. Yeah. Put 9/8 to the 8th. Products over reactants. Products over reactants. Okay, I got about 166. But to do that, you got to know how to raise this guy to the 8th power, right? If you have one of these calculators, all it's going to be is you put in 0.98 and find x to the y. There it is. You can raise it to whatever power you want. So I'm going to push it, and then 8. And that's 0.98 to the 8th power. You get about 0.85. Okay, so do that part first, then do the rest. So the we definitely don't have 200. The reaction is going to shift towards the right, which is the products. Okay. So write the big K expression. And what they want you to do is, if it's a gas, they don't want you to use brackets. Because gas, the standard state is 1 bar. So you have to have units of pressure. It's not molarity. So if you see a gas, now there isn't a gas in this first one, but there is in this one. So just write the K expression for both of these. See if you match, or ask somebody. We're running out of time. So it looks kind of odd, but that's what they want. They want capital P's with subscripts for the gases. And the units need to, again, the units need to be bars. If you've never heard of a bar, well, what is it? I think it's 1.01325 pascals is a bar, I believe. I think that's, I would Google it. But I think that's, if you need it, something like that. Or no, you use ATMs. You're used to ATMs, aren't you? I think that's it. I think there's 1.01325 atmospheres in a bar. I think. I'm pretty sure. In fact, I can tell you. Oh, I don't have my book. Okay, but I'm pretty sure that sounds about right. So come by if you have some questions. There's always more than, this is just another Le Chatelier problem.